Hello everyone. So this time we're gonna discuss the matrices for linear transformation. So in this section we're gonna find the matrix of a linear transformation with respect to the standard basis. So if you can still remember the standard basis for matrices or the identity matrix, so we have 2 by 2, that is 1 0 0 1, and we have 3 by 3, that is 1 0 0 0 1 0 and 0 0 1, and so on. Suppose we have a matrix A with elements -1, 4, 0, and 1, -2, and 5, and let V be equal to x, y, and z, and we have the transformation of our vector V, which is equal to the product of our matrix A and V. Then we have the transformation of vector V is equal to the product of matrix A and V is equal to -x plus 4y and x minus 2y plus 5z. Or equivalently in function notation, that is the transformation of xyz, that is our vector V elements, is equal to x minus 4y and x minus 2y plus 5z, which is the product of matrix A and vector V. So just like in matrix, the standard basis for Rn written in vector notation is B is equal to the set of vectors E sub 1, E sub 2, up to E sub n, the set of vectors which forms diagonal 1 or which forms identity matrix. So in order to find the standard matrix for linear transformation, we will let the transformation of Rn to Rm be a linear transformation such that the transformation of vector E sub 1 be equal to A sub 1 1, or that is row 1, column 1, A sub 2 1 up to A sub m 1, and the transformation of vector E sub 2 be equal to A sub 1 2, A sub 2 2 up to A sub m 2, up to the transformation of the vector E sub n equals A sub 1n, A sub 2n up to A sub mn. Then the matrix whose n columns corresponds to the transformation of E sub j, and that is our matrix A, which composed of the vectors that we have generated. And matrix A is called the standard matrix for the transformation. So to further understand, let us have an example. So what is the standard matrix for the linear transformation? R3 to R3 defined by the transformation of x, y, z is equal to 2x plus y, 3x minus 2z, and -z. So just like in our previous lessons, if we're going to put this transformation in vector form, we're going to take the values of our x, y, and z. So from this function notation, we will get the transformation of E sub 1, E sub 2, and E sub 3. So in this parenthesis, we have the value of x, which is 1, 0, and 0, equals, so here we have 2, 3, and 0. And we have the transformation of vector E sub 2, that is y. So we have here 0, 1, 0 equals, so we have 1, 0, and 0. And the transformation of our E sub 3, so we have z, 0, 0, 1 equals 0, -2, and -1. So if we're going to put this into vector form, we will have 2, 3, and 0, 1, 0, 0, and 0, -2, -1. So by the theorem M by N matrix, that will be matrix A is equal to this vector. So we have 2, 3, 0, 1, 0, 0, and 0, -2, -1. And this is now the standard matrix for transformation. So now let's get into the composition of linear transformation. Let the transformations T sub 1 from Rn to Rm and T sub 2 from Rm to Rp be the linear transformation with standard matrices A sub 1 and A sub 2. The composition of the transformation Rn to Rm be defined by the transformation of vector V equals T2 times the quantity T1 times V, or the transformation of the vector is a linear transformation. Moreover, the standard matrix A for the transformation is given by the matrix product A is equal to A sub 2 times A sub 1. So to further understand this, we're going to have an example. So for example, let T sub 1 and T sub 2 be linear transformations for R3 to R3 such that T sub 1 of xyz equals x minus y, x plus y, and x minus y minus z, and T sub 2 of xyz is equal to x, -2y, and 3z. So first, we are going to determine the standard matrices for the composition of transformation equals T sub 1 of T sub 2. So first, we are going to take the values of x, y, and z for the transformations T sub 1 and T sub 2. So we have here two matrices A sub 1 and A sub 2. So in matrix A sub 1, we have x values of 1, 1, 1, and y values of -1, 1, and -1, and z value of 0, 0, -1. In matrix A sub 2, we have the x value of 1, 0, 0, y value of 0, -2, 0, and z value of 0, 0, 3. So let's put this into a matrix. So these are the vectors of each transformations, and we have to put this into matrix. And these are now the standard matrices for each transformations. We have matrix A sub 1 and matrix A sub 2. And now we're ready to take their compositions. So if matrices A sub 1 and A sub 2 are the standard basis for linear transformation, and it is defined that we will get its linear transformation by getting its composition, that is T sub 2 times the quantity T sub 1 times V. So meaning we have to get into its transformation matrix, which is the product of A sub 2 and A sub 1. So we will use these two matrices in finding the transformation. So if these are the standard matrices and we're going to find the matrix A, which is the product of these two matrices, so we're just going to multiply these two matrices. So in getting the composition of these two, we're going to multiply the rows of A sub 2 by the columns of A sub 1. And then after that, we will get the sum of the products. Okay, so let's start with 1. Multiply to 1, so that is 1. Let's put parentheses. Plus, we have 0 times 1, so that's 0. 0 times 1 plus 0. So this will be the first element of the matrix A. And then this row with this column. So we have -1 plus 0 plus 0. And then this row by this column, we have 0 plus 0 plus 0. And next, we'll multiply this row by this column. So that's 0 times 1, that's 0. Negative 2 times 1, that is negative 2. Plus 0 times 1, that's 0. And this row by this column, so that's 0, negative 2, and 0. So next, this row by this column, so that's 0 plus 0 plus 0. And then the third row will be multiplied to the first row, so that's 0, 0, and 3. The third row times the second column, so that's 0 plus 0 plus negative 3. And third row by third column, 0 plus 0 plus negative 3. So the matrix A now, which is equal to the product of A sub 2 and A sub 1, is equal to 1, negative 2, 3, negative 1, negative 2, and negative 3. And lastly, we have 0, 0, negative 3. So this is now the standard matrix for transformation. Okay, so let's get into the inverse of the linear transformation. So if the transformations T sub 1 from Rn to Rn and T sub 2 from Rn to Rn are linear transformations such that for every V in Rn, T sub 2 of T sub 1 of V is equal to V, and the T sub 1 of T sub 2 of V is equal to V, then T sub 2 is the inverse of T sub 1 and T sub 1 is invertible. So if T is invertible with the standard matrix A, then the standard matrix for the inverse of the transformation is denoted by the negative matrix A. So let's get into an example. So example, let a transformation of Rn to Rn be a linear transformation defined by the transformation of x, y, z is equal to 2x minus y minus 3z, 3x minus y minus 2z, and negative 4x plus y. So show that it is invertible and find its inverse. So with this function notation, we are going to write it first into a standard matrix. Okay, so our standard matrix is, so we have x, y, and z. So we have 2, 3, and negative 4. For y, we have negative 1, negative 1, and 1. And for z, we have negative 3, negative 2, and 0. So this is now the standard matrix of this function notation. So now we're gonna find its inverse using the techniques of inversion. So in our previous lessons, we have already discussed determinants and cofactors. So we're gonna use that in finding the inverse of a matrix. So in finding the determinant of a matrix, isn't it that if it is 3 by 3 matrix, we're going to write down the first and second column on the right side of the matrix. So that is 2, 3, negative 4, negative 1, negative 1, and 1. In order to complete the diagonals that we are going to make later. Okay, so this is, so next step that we are going to do is we are going to get the products of the diagonals. So let's first take this diagonal. So that is 2 times negative 1 times 0 is 0. Then negative 1 times negative 2 times negative 4. So that is negative 8. And then we have negative 3 times 3 times 1. So that is negative 9. And then we're going to take the opposite diagonals. We have here negative 4 times negative 1 times negative 3. So that is negative 12. Then next we have 1 times negative 2 times 2. So that is negative 4. Then lastly, we have 0. Next, in order to find the determinant of our matrix, we will just subtract the sum of the products of the diagonals. So we have 0 plus negative 8 plus negative 9 minus negative 12 plus negative 4 plus 0. So 0 plus negative 8 plus negative 9 is negative 17 minus negative 12 plus negative 4 plus 0 is negative 16. So the determinant now of our matrix A is negative 1. So we are going to use this later in finding the inverse of the matrix. So looking back in our matrix, the next step that we are going to do is to find its cofactors. So we've already discussed that. So in finding the cofactors, so in every element, we're going to cancel out every vertical and diagonal elements that align to it, and then get the remaining elements in the matrix. So that in our first element, we have negative 1, negative 2, and 1, 0. And then for the second element, we have, so we're going to cancel this and this one. So what remains now is 3, negative 2, and negative 4, 0. So for the third, we're going to cancel this row and this column. So what remains now is 3, negative 1, negative 4, and 1. So we're going to do the same process to all the elements. So next, after this, we're going to cross multiply each element of a cofactor. So that's negative 1 times 0. Then we will subtract the product of 1 and negative 2. So negative 1 times 0 is 0, minus negative 2 times 1. So 0 minus negative 2 is positive 2. So we will do the same on the remaining elements inside the matrix. So to cut it short, we got this matrix. But we have the rules and signs in getting the cofactors. So we have to change the signs of each element in our matrix. So let's start with positive, negative, positive, and then negative, positive, negative. And lastly, we have positive, negative, and positive. So that's still positive 2. Now it's positive 8, negative 1, negative 3, negative 12, positive 2, negative 1, negative 5, and positive 1. So these are now the cofactors of the matrix. But we're not done yet. So in order to find the inverse of the matrix, we're going to flip the elements of this matrix except on this diagonal. So let's have another matrix here. So let's now get the inverse of the matrix. So 2, 12, negative 12, and 1 remains on their place. So let us now flip the elements. So 8 here and negative 3 will change their positions. So this is negative 3 and this is 8. And so with negative 1, still the same. Negative 5 and 2. But we're not done yet. So in order to find the inverse of the matrix, we're going to multiply this by 1 over our determinant. So what is our determinant a while back? That is negative 1. So that will be multiplied by 1 over negative 1, or simply by negative 1. If we are going to multiply every element in the matrix by negative 1, that will be negative 2, 3, 1, negative 8, 12, 5, 1, negative 2, and negative 1. So this is now the inverse of our matrix. So since the inverse of the matrix A exists, it follows that the inverse of the transformation also exists. And that only means the inverse of our transformation of x, y, and z is equal to 2x plus 3y plus z, following the values in our matrix, minus 8x plus 12y plus 5z, and x minus 2y minus z. That is in function notation. And that means it is invertible.